Okay, fine. So since I mentioned these things, of course, I mean, these are just, I personally believe it is really important for you to know these gentlemen, because this will give you an idea that these days we are actually talking about standard model, and we are even talking about beyond the standard model very casually. But people, the great scientists, they have spent their lives in discovering or formulating the theory the way at least we are treating the standard model right now. So they are the founders of the Hogwarts of particle physics, which is the standard model, and main credit goes to these three gentlemen, Glashow, Weinberg, and Salam. So they are the founding members of the standard model, and as you can see, all of them are awarded with the Nobel Prize. And finally, after that, they just proposed a part of the, in fact, what these three gentlemen proposed around 1960, that was only known as the electroweak model. But later came the pioneering contribution from David Gross, Politzer, and Wilczek, and also from Etuf and Veltman, and also Nambu. And these six gentlemen, unfortunately, only Peter Higgs and England managed to bag the Nobel Prize. But all these people collectively, they helped to form the theoretical backbone of the standard model. And it is a bit unfortunate that Hagen, Kibble, and Gurandling, their names were left aside. Robert Brown died before the Nobel Prize, but unfortunately they are still alive and they failed to get the prize, but they also have equal contribution. And as you can see, that the theory of the Higgs boson were postulated or formulated by this gentleman in 1964. And this is also another important slide. I don't prefer to spend a lot of time in this slide, but you should know the seekers of the standard model who help to discover each and every particle, or to predict the existence of each and every particle, which are the basic ingredients of the standard model. So, and one more interesting thing, what you should see, the starting from 1897, when electron was postulated theoretically, and eventually it was discovered by J.J. Thomson by 1906. And you see, eventually it took us more than 100 years. So finally in 2013, we have the Nobel Prize for the Higgs boson discovery. So it's a long journey. So some of you may have this kind of feeling that standard model is the end of the story, but as I will show you through this talk, that this is not the end of the story, and maybe we need to wait for another 100 years to discover something beyond the standard model. If it itself, it has taken 114 years to discover the entire particle spectrum of the standard model. So you can understand that if you want to probe something beyond, it is really challenging. And since I'm going to talk about the neutrino, so I would like to mention this gentleman. In 1956, they discovered this electron neutrino, and for that they deserved their Nobel Prize in 1995, Cowan and Raines. And there were two more neutrino prize, Nobel Prize associated with the neutrino. In fact, three, which is actually due to the discovery of the muon neutrino. The credit goes to the Leatherman, Schwarz, and Steinberger. And in fact, since one of you mentioned about this God particle, so this man is the culprit behind this name God particle. In fact, those of you who are interested, the name of the autobiography of Leon van Leatherman is known as the Search or Quest for the God particle. So he is the man who made this name famous. Okay, moving forward. So after a journey, or I would say after a rigorous journey of 114 years, when we have discovered or detected the Higgs boson, naturally, it is now legitimate to ask, is this the end of the story? Because with the discovery of Higgs boson or Higgs particle, we have discovered each and every single ingredients of the standard model. So it seems like it's a happy ending and we don't need to consider anything more. But unfortunately, this is not the end of the story, because there are certain questions which yet remain unanswered. For example, experimentally, the time when this gentleman proposed the neutrino physics, proposed the theory of the standard model, that point of time, the masses of the neutrinos were not discovered. So, in the original standard model, as it was proposed by this gentleman, so these people, these guys, neutrinos are exactly massless. But later, people have observed or detected the presence of massive neutrinos. How? That is the core of this of today's talk. And there are certain other glitches. For example, who ordered the mass of the Higgs to be 125 GeV? Why not 20 GeV? Or why not 500 GeV? Or why not 1 TeV, 1000 GeV, or more than that? These particular questions remain unanswered. Of course, as I said, that it's a bit difficult to understand at your present level, because the thing is that at the end of the day, when you are studying particle physics properly, you are actually working in the regime of the quantum field theory. Now, it turns out in the regime of quantum field theory, you have certain untamed correction which have a tendency to blow up the Higgs mass to a very high value. But the physically measurable Higgs mass is only 125 GeV. So now the question that scientists ask is that, in spite of such large correction, why the mass of the Higgs is only 125 GeV? This is often known as the fine-tuning problem, but this is not on today's menu. Then more question: what is dark matter? We know like several dark matter experiments are going across the globe, but is there any dark matter in the standard model? The answer, unfortunately, is no. And also there are other glitches, like why we have more matter than more antimatter. So these are the collective questions which will eventually compel you to go beyond the standard model. So, as I said, today I'm going to consider only about the massive neutrinos, and what is really interesting, that out of all these glitches which I mentioned here, why there is more matter than more matter than antimatter? Okay, maybe the nature is perverse in nature, and that's how it is. Okay, what is dark matter? We really don't know. Maybe it is something that is beyond our understanding or beyond the scope of our current level of understanding of particle physics. Why mass of the Higgs is 125 GeV? Maybe nature likes fine tuning. But whatever be your logic, you cannot deny the presence of massive neutrino, because this has already been observed, and that is related to a particular thing which is known as the neutrino oscillation. And as you can see, that the theory was formulated long back. In fact, it was first time formulated in 1957 by Bruno Pontecarvo. But you see that finally this gentleman, McDonald and Kajita, they earned the Nobel Prize for detecting this or confirming this experimentally. So 2015 Nobel Prize was awarded for the experimental discovery of neutrino oscillation. Now, as I will show you that this oscillation is impossible if you do not consider massive neutrino. But as I just pointed out, or if I go back, as you can see, in the original standard model, the neutrino is massless. So, first of all, why neutrinos oscillate or how neutrinos oscillate, that is itself a challenging thing. More importantly, compared to that, the experimental verification of neutrino oscillation undoubtedly compels you to think about the fact that there exists physics beyond the standard model. So I will take a few seconds pause here. So if you have any questions or comments and doubts, just let me know.
Sir,
Yes, please.
is there any valid theory regarding parallel universe?
As of now, there exists some mathematical formulation. See, as of now, in fact, what you ask, this is in a sense not exactly the, I mean, how this is connected, I mean, how today's talk is connected with the parallel universe, but some of the question that you ask is related to the philosophy of today's talk. Why I am talking about massive neutrinos and not about any other thing? Because existence of the massive neutrinos, as I just said, is experimentally observed. But how neutrinos, they are getting their masses, it's yet unknown. And that is the reason why you have several thousands models. But which one is the correct one? As of now, we have no clue. Maybe future will tell us the answer. Anything more?
What exactly is antimatter?
So antimatter is something like, you know about the electron. So the antiparticle is like positron. So basically, matter antimatter, I mean, if you believe this kind of fascinating sci-fi fact, then it is something like another entity which is composed. So if you are composed of the particle, and if there exists another entity which is composed of the antiparticle, it will be your antimatter. And as per the sci-fi, when matter meets antimatter, they explode and you will only have energy. And that is something similar like if you have electron positron, then you will only get photons.
Okay, sir.
As of now, why, as I just mentioned, like why there is more matter than antimatter, it's not clear. In fact, if you are interested in studying particle physics, you will see later there are certain mechanisms to reproduce some of the, I would say, some of the observational, like observed fact, but what is the exact mechanism? It is not known.
Okay, sir.
Okay. Because, yes, please.
Sir, is this Neutrino oscillation, is this a theory or is it verified?
Neutrino oscillation has been observed in nature.
Has been observed. But sir, yes, I've heard that it is difficult to detect neutrinos even. So how do you check?
Don't worry. I will discuss all about this thing. So don't worry. Those are on today's menu. Of course, I cannot explore all the details because then it is going to be like several hours. It will run for several hours, but I will give you the glimpse. It is true what you mentioned. It is really, really extremely difficult to detect the neutrinos, and why I will explain you in a while. Okay. So now the first things, as I mentioned, that what do you mean by neutrino oscillation? So to know what is the meaning of neutrino oscillation, let me give you two examples, which were the two cases which first time gave us the idea or the fact that there is something wrong with the neutrino flavors. So for example, if you consider sun, now inside the sun, in this tremendous temperature and pressure, there is something which is called the PP cycle. I'm not going into details, but there the protons are converted into helium and it emits a few positron, which is denoted by E plus, and a few electron neutrino. Now, let me answer your question. These neutrinos, when they meet a nucleus, they will give you back an electron and another nucleus. In fact, you can think about this as a inverse beta decay process. So what actually is happening, suppose you consider this as a nucleus, and you consider a high energetic. So let me give you some more simple example. Suppose you have a ball, a big ball, a big iron ball, and suppose you are actually throwing ping pong ball towards it. Now, if you are throwing one ping pong ball, two ping pong ball, nothing will happen. But all of a sudden, if you started throwing millions and billions of ping pong balls, at some point of time, because of this collision, although each collision is going to transfer minimum amount of momentum transfer to this big target, but if you consider large amount of interaction, at some point of time, this will move slightly. And more importantly, apart from that, in this process, there is this. Now, this movement is so small, it is extremely hard to detect experimentally. But then, who is going to save the day? It is this electron who is going to save the day. So normally what you mentioned, like the typical way how they detect, I am going to give you one example. That is the people normally put a lot of heavy water, D2, in the pot. So when neutrino beams are coming, say from sun, they interact with these things, with this heavy water, and eventually they produce this, some, at least because it is a huge number of neutrinos, maybe 10 to the power 40 or 50, some of them may produce some charged electron. Now this electron, these are being, because of the fact that they are charged particles, you can actually detect them. And of course, before that, you have to make sure that in your theory you have, or in your experiment, you have no other source of getting the electron. The moment you are going to detect that electron, that is a fact, or that is a kind of confirmation that there is an interaction involving one neutrino. But unfortunately, that means what you would expect from this reaction, you would only expect electron. Somehow there are theoretical calculations by which you can actually calculate, depending on the number of incoming neutrino flux, you can actually calculate the number of electron. Of course, the calculation is really, really complicated. But unfortunately, when scientists observed the number of the electron detected and anticipated, they were not the same. In fact, only 1/3 of the event, of the expected event, were detected. And that particular phenomenon is known as the solar neutrino anomaly or solar neutrino problem. Similarly, in the sky, I mean, this is a natural source of cosmic rays. So cosmic rays are pion. And I'm sure that all of you heard about the pion. All of you know about pion, I guess. Charge pion. Some idea about pion?
No.
So what?
Pion, P-I-O-N, pion, charge pion.
No.
Okay, so pion is basically another elementary particle, and one of you actually asked me this question about this the composition of this neutron and proton. So basically, in the nature, this quarks contain into two states typically. One is as the bound state of 3 quarks, which is typically the proton and the neutron, but there is another possibility which is the bound state of 2 quarks. They are known as the mesons. For example, if you consider a quark like UD bar, so 2/3 minus of minus 1/3, and that is going to give you how much? 1. That is actually nothing but pi plus or positively charged pion. Now it turns out that these pions, when they are coming, so there exists an abundance of pion in the cosmic rays. They actually decay. And a pion typically decay into one muon and one muon neutrino. Because if you go back, as I showed in this elementary, in the slides of this elementary particle, so we have 3 neutrinos and each of them are associated with the corresponding flavor or corresponding type of the charged lepton. So corresponding to electron, you have electron neutrino, corresponding to muon, you have muon neutrino, and corresponding to tau, you have tau neutrino. Okay. Now this muon, while traveling, because as you can understand that from the cosmic scale, because all the detectors are actually placed on the Earth. So in this long travel path, not only the charged pion decay into a muon and a muon neutrino, a muon also undergoes further decay, and the decay of a muon produced 3 final states: a charged electron, a muon type neutrino, and an electron type neutrino. So if you consider decay of one charged pion, you will expect 2 muon neutrino and 1 electron neutrino. So the ratio must be 2 or nearly equal to 2, because you have some problems or some glitches or some limitation in your experimental setup. But overall, the expected number is 2. But in reality, it was way below number 2. So that is roughly known as the atmospheric neutrino problem. So in order to solve that, people immediately thought that maybe somehow while traveling, we are actually losing a particular type of the neutrinos. And why it is? Because if you consider this experiment was designed to detect electron. In fact, you can replace this entire relation with a muon neutrino, which will actually produce a charged muon. But suppose you have your experiment, which is designed to detect only electron, then probably it is not going to, it is not possible for that to detect muon, at least not to that accuracy. So that means if you are detecting only electron, so it seems for you something is wrong. Why I am not getting the anticipated number of events as I can extract or calculate using theoretical model. So this loss of neutrino flavor, certain flavor, is related with the mechanism of the neutrino oscillation. And that is the reason, just like the shifter, I have identified the neutrinos as the boggart of the standard model of particle physics.